hope this video will help you to know about oxidation number and its calculation. Let us take an example, SO4 2 minus. In SO4 2 minus, the oxidation number of sulfur is found to be plus 6. You see, x plus 4 into minus 2 is equal to minus 2, x minus 8 is equal to minus 2, x is equal to plus 6. Minus 2 is the charge on sulfate ion and minus 2 is the oxidation number of oxygen. In potassium dichromate, the oxidation of chromium is found to be plus 6. You see, for potassium it is plus 1 into 2, for chromium this is 2x, for oxygen it is 7 into minus 2 is equal to 0. 2 plus 2x minus 14 is equal to 0, 2x is equal to 14 minus 2, or x is equal to 12 by 2 plus 6. HCl is a covalent compound, but here we have to assume HCl as an ionic compound. HCl as an ionic compound. In HCl, the oxidation number of hydrogen is plus 1 and the oxidation of chlorine is found to be minus 1. As it is electropositive and it has one valence electron in its outermost shell, its oxidation number is plus 1, and for chlorine it is x plus 1 plus x is equal to 0, x is equal to minus 1. In case of sodium hydride, the oxidation of hydrogen is minus 1. 1 plus x is equal to 0, x is equal to minus 1. In sodium hydride, the oxidation number of hydrogen is minus 1. Here hydrogen is more electronegative, but here hydrogen is more electropositive. When it is electropositive, its oxidation number is plus 1. When it is electronegative, its oxidation number is minus 1. In elemental state, the oxidation of hydrogen is 0. Oxidation number of hydrogen is plus 1, minus 1 or 0, plus 1 or minus 1 or 0. In plus 1 in HCl, minus 1 in sodium hydride, 0 in elemental state. Oxidation number of hydrogen in copper hydride. In copper hydride it is plus 1, in silver hydride it is plus 1. In copper hydride, the oxidation of copper is minus 1. In sodium hydride, the oxidation of hydrogen is minus 1 because here hydrogen is more electronegative than sodium. But in silver hydride, hydrogen is more electropositive than silver, so its oxidation number is plus 1. In case of fluorine, the oxidation number is minus 1 in all its compounds, because fluorine is the most electronegative element and its oxidation number cannot be positive 1, and minus 1 can be calculated by subtracting 8 from 7. 7 is the number of valence electrons. 7 minus 8 is equal to minus 1. And in elemental state, the oxidation number of fluorine is found to be 0. Oxidation number of chlorine in all its compound, oxidation of chlorine is minus 1, 0, plus 1, plus 3, plus 5, plus 7. Minus 1 is the minimum oxidation state. It can be calculated by subtracting 8 from 7. 7 minus 8 gives minus 1. 7 is the number of valence electrons. 0 in elemental state, plus 1 in ClF, plus 3 in chlorine trifluoride, and it has plus 7 oxidation state, and it is the maximum oxidation state. And you know chlorine has 7 valence electrons in its outermost shell, so maximum oxidation state is plus 7. For sulfur, the oxidation state is minus 2, plus 4, plus 6. Minus 2 can be calculated by subtracting 8 from 6. 6 minus 8 is equal to minus 2. As it has 6 valence electrons in its outermost shell, its maximum oxidation number is also plus 6. In case of oxygen, the oxidation states are minus 2, minus half, minus 1, 0, plus 1, plus 2. Minus 2 when 8 is subtracted from 6. Minus half in superoxides, minus half in superoxides, minus half in superoxide KO2. Minus 1 in peroxides, 0 in elemental state, plus 1 in O2F2, plus 2 in OF2. You see, in OF2, fluorine has minus 1 into 2 and oxygen has x minus 2 is equal to 0, x is equal to plus 2. Its oxidation number cannot be more than plus 2 because of absence of vacant d orbital. You see, oxygen and sulfur are in the same group, but maximum oxidation number of sulfur is plus 6, whereas in case of oxygen, the maximum oxidation state is plus 2. It cannot be more than plus 2 because of absence of vacant d orbital. In group 1, the elements are sodium or potassium, lithium, sodium, potassium. These are alkali metals. Let us take sodium as an example. The oxidation state of sodium in all its compound is found to be plus 1. Similarly, the oxidation state of potassium in all its compound is found to be plus 1. Usually these elements are electropositive, relatively more electropositive than the other element with which it combines. In uncombined state, the oxidation state is found to be 0. In case of calcium or magnesium, the oxidation state of calcium or magnesium is found to be plus 2 in all compounds. And you know, calcium and magnesium are relatively more electropositive than the other element with which they combine. Whereas in case of aluminum, the oxidation state is plus 3, and in uncombined state it is 0, like alkali and group 2 elements. But in group 13, thallium is the heavier element and it shows +1 and +3. +1 is due to inert pair effect. +1 means here ns2 electrons do not take part in bonding and only np1 electron takes part in bonding. But +3 when both ns2 and np1 electrons take part in bonding. In aluminium, both ns2 and np1 electrons take part in bonding, but in thallium only np1 electrons take part in bonding in +1 oxidation state. So +1 is due to inert pair effect. This pair is inert, means inactive in the formation of bonds. As it is inactive, this pair is known as inert pair and its effect is inert pair effect. Because of inert pair effect, it shows +1 oxidation state. You see +3 and +1, the difference between these two oxidation state is 2 and that is due to this ns2. For heavier elements like thallium in group 13, +1 is more stable, and for lighter elements like aluminum, +3 is more stable. Oxidation number of Mn in KMnO4 is found to be +1. You see +1 plus x minus 2 into 4 is equal to 0, 0 as it is neutral. +1 plus x minus 8 is equal to 0, x is equal to 8 minus 1 plus 7. In case of CH2Cl2, the oxidation of carbon is found to be 0. X plus 2 into +1 plus 2 into -1 is equal to 0. -1 for chlorine, +1 for hydrogen. X plus 2 minus 2 is equal to 0. 2 minus 2 cancelled, so x is found to be 0. In case of H2SO8, the oxidation of sulfur is found to be +6. As it has 6 electrons in its valence, so it cannot show oxidation state more than +6. Maximum oxidation state of sulfur is found to be +6. In H2SO8, there are 2 oxygen atoms linked to each other by peroxide linkage, and this compound can be written as HOSO2OO SO2OH, or you can say H2O2O6. There are 8 oxygen atoms. Here I have written O2O6. These 2 oxygen atoms are linked by peroxide linkage. Now we can calculate the oxidation of sulfur as shown over here. H2 +1 into 2, for 2 sulfur 2x, for these 2 oxygen atoms 2 into -1, for these 6 oxygen atoms it is 6 into -2 is equal to 0. As it is neutral, it is 0. 2 plus 2x minus 12 minus 2 is equal to 0. 2 plus 2x minus 14 is equal to 0. 2x is equal to 12, or x is equal to 12 by 2 plus 6. It cannot be more than +6 because of it cannot be more than +6 as it has 6 valence electrons in its outermost cell. Let us take another example, H2SO5. It has 2 oxygen atoms linked to each other by peroxide linkage. So H2SO5 can be written as H2SO3O2. The oxidation number of S can be calculated. You see +1 into 2 for 2 hydrogen atoms. For S it is x. For 3 oxygen atoms this is 3 into -2, and for these 2 oxygen atoms 2 into -1 is equal to 0. -1 means peroxide linkage. So 2 plus x minus 6 minus 2 is equal to 0. 2 plus x minus 8 is equal to 0. Or 2 minus 8 plus x is equal to 0, or minus 6 plus x is equal to 0, x is +6. So oxidation number sulfur in H2SO5 is found to be +6. Let us take another example, potassium ferricyanide K3 Fe6. That is a complex compound. In complex compound, the oxidation number Fe can be calculated. You see, for potassium it is +1 into 3, for Fe it is x, and for cyanide it is -1 into 6 is equal to 0 because it is a neutral compound. Cyanide has -1 oxidation state. So +3 plus x minus 6 is equal to 0, plus x minus 3 is equal to 0, x is equal to +3. This compound is known as potassium hexacyanidoferrate 3. Potassium hexacyanidoferrate, Roman letter 3 in bracket. Oxidation number of hydrogen in copper hydride is +1 because hydrogen is more electropositive than copper. In sodium hydride, the oxidation number of hydrogen is -1 because hydrogen is more electronegative than sodium, as shown in the electrochemical series. At the top you will find electronegative elements, at the bottom you will find electropositive elements. Oxidation of bromine in Br3O8. You see, for 3 Br atoms 3x, for 8 oxygen atoms it is -16 is equal to 0. 3x is equal to plus 16, X is equal to plus 16 by 3. Here you see each bromine is connected to oxygen atoms as shown. First bromine connected to 3 oxygen atoms, so its oxidation number is plus 6 because these oxygen atoms carry minus oxygen state. In this case, bromine carries plus 4 oxygen state because these two oxygen atoms carry plus minus 2. Here in this case, this bromine carries plus oxygen state because these 3 oxygen atoms have minus oxygen state in each case. So average oxygen number of bromine is plus 6 plus 4 plus 6, 16 by 3. And the difference between two different oxygen states in bromine is found to be 2. 6 minus 4 is equal to 2. Oxidation number of D block elements can be calculated by knowing its electronic configuration. Let us take an example, manganese. In case of manganese, the oxygen states are plus 2, plus 3, plus 4, plus 5, plus 6, plus 7. As you know, both S and D electrons take part in bonding in case of D block elements. The oxidation states are plus 2, plus 3, plus 4, plus 5, plus 6, plus 7 for manganese. 4s2, 3d5, 7 electrons, and each S and D electrons take part in bonding. In case of copper, the oxidation states are plus 1, plus 2. In case of iron, it is plus 2, plus 3. In case of Sc, it is plus 3 only. In case of zinc, it is plus 2 only because 4s2 electrons take part in bonding. Whereas actinides have a large number of oxidation states because 7s, 6d, 5f have comparable energies. As they have comparable energies, electrons from all these subcells take part in bonding. 7s, 6d, 5f. Lanthanides have plus 3 common oxidation state. It shows plus 2 and plus 4 in some cases. Thank you.